This is a problem-solving workshop. I'm Dave Princehorn, one of the coordinators of the Library Learning Commons Math and Science Lab at South Campus. And today we're going to take a look at a number of different subjects and how to approach solving problems, word problems, in those subject areas. The majority of the technique we're going to talk about is an algebraic approach to solving these problems. Now, you can think about it all different types of ways you can solve problems. I mean, in everyday life, we figure out, how to handle our bank accounts and how to enroll in classes. That's all problems that we solve every day. The kind we're going to look at today involve a lot of the same thing, understanding what the heck is you need to do in order to address the problem, and then devising a plan, going about doing it, and seeing if you actually did what you said you needed to solve, or looked at what you needed to solve. So all of those things that we do in everyday life, we also do in the homework assignments that we have, often that deal with word problems and problems in science and math. So this is a guy that often one sees when you first start problem solving in your textbook. He's been around since many, many, many years. Back in the 40s, I think, is when this guy put forth his 4 steps of problem solving, POLIA. And they still apply today. Understand the problem. We're going to find that takes up a huge chunk of the problem solving process because, first of all, the problem usually is stated to us in our own language of some sort, in English, or if we speak English. And we have to kind of interpret that, what that person is asking us to do, or what the problem in the book is asking us to do, into some form that we can work on, devise a plan for, carry out a plan, and then look back and see if we answered what the original question was. But if we don't know what the original question is, we can't go any further. So understanding what the question or problem is important. Now, it would be so nice if you could go step by step, understand the problem, check, devise a plan, check, carry out the plan, and then look back and you'd be done. Unfortunately, problem solving is not often a step-by-step process. You might try to understand the problem and then move on to devise a plan, and you find out that you don't have the skills for that plan, or maybe that plan isn't quite addressing the problem as you thought it was going to. So you got to go back and try to understand the problem again. Maybe you got all the way down to the end and you found an answer, but then you look back and it really didn't, it didn't answer the original question. You did all your mathematical stuff and you got a number, and that number somehow doesn't make sense when you get to the end. So this process is one where you go back and forth. You try plan A, it doesn't work. You try plan B, it doesn't quite work. You try plan C, it doesn't work. Then you go take a nap for a little bit. Hopefully a light bulb will come on while you're, while you take a break. And then you come back and try again. Now, back in the day, you may not have this type of problem yet, but sometimes there were problems that would take a week just to get, for me, that I used to do, it would take a week just to get a sense of, to understand the thing, and then, to actually write it up and figure out a way to solve it. So those are true problems. Those are the problems that often in real life one has. You try to come to terms with it, devise a plan for it, carry out that plan, look back. And like I said, that may take a number of iterations in order to do that. Okay. Here's an example. We're going to focus basically on algebraic approaches as our plan for many of the problems we're going to look at today. But there's other types of plans that one could devise. For example, you could have simulations or experiments, to help you solve a problem. And you could program those maybe into a computer. It would run its thing and help you solve that problem. You could use a bit of logic, thinking it through, devising ways that make sense and don't make sense. Without writing out an algebraic expression at all, possibly, and come up with a solution to your problem, okay? But we today are going to be looking at the algebraic approach to solving problems for the most part. And having said that, one of the skills one needs in order to do that, of course, is that translation. As I said, often the tough part is understanding the problem. So that's starting with the problem written or given to you either verbally or written on a piece of paper or out of your book or off the computer, and then trying to translate what the heck it's asking you to do. And so there's going to be some key phrases one has in order to translate that written language or spoken language into an algebraic form that we can then, of course, use our skills, our algebra skills, in order to hopefully solve and come up with an answer to our original problem. So, for example, here are some keywords: add, sum, increased by, greater than, excess of, combined with. All of these words have to do with a certain operation in mathematics. And that operation, of course, I don't think we have to stretch our imagination too far, but that operation, of course, is addition. And here is what you'd expect. Next keywords. Well, this one, if that's addition, less than, difference of, decreased by, reduced, difference between, fewer than. Well, that's, of course, going to be subtraction.
I don't know if you were waiting for me to answer the question, but it is a subtraction, yes.
Sorry, Oksana. Yeah, what is it?
It's subtraction, yes, you're right.
Okay, good. Oh, yes, I like the interaction. Thank you. And the next one, what's it? Product, times, multiplication.
Multiplication.
Yeah, it actually had the word right in the multiplied by, of course, means multiplication.
Okay, multiplication.
So that keyword. And of course, this is running down through all the 4 different operations, basic operations that we have, that when we do this. So the next one, of course, is going to be division, and I'll put that in there.
Okay.
And look at the keywords that go along with that. Now, there's some tricky ones in here. For example, per. If I said, I might have this amount of money per that many gallons. What does that mean? Well, that means you take a division. That means that much money divided by how many gallons I have, and then you have a price per gallon, possibly. Okay? So that per, ratio of, quotient is a big one. Some students don't, they see this word, this vocabulary, and they get stuck. It means division. So division. And often we'll use a slash symbol, or we use the division symbol when we have division. And of course, the last one is a relationship. And we're going to have different symbols for different types of relationships. This relationship here is, of course, the equality, which is used for a lot of the different models that we have for a problem that we're doing. We might write an equation to express what's going on in that problem, and then solve that equation, and then we've got a solution to our problem, possibly. So this is going to be equal. And so there are some keywords that go along with that. Equal to, result, is that little word is, often can be translated as equal. Okay. Right. Now, using those ideas, let's put them together into a sentence and try to interpret what this is. Now, once again, this is just a tool that we have for solving some of the math problems that we might run into. And science problems, they're couched also in this type of language. So I'm going to let you try this first one. 16 subtracted from 5 times a number equals a number plus 4. These drive some people crazy when they see those. Now, we're going to find a technique that's very important when we do this, and that's to identify the unknown. So, Oksana, what is the unknown if we can express it in words, what is the unknown here?
So we have 16 subtracted from 5 times a number. So unknown is the number.
Number is the unknown, right? So yeah. And often, come on, my board has gone crazy because my mouse is trying to do two things at once. All right, let's see if I can do this without my mouse.
The number equals the number plus 4.
Yeah, so what I'm going to do is I'm going to do something abstract. I'm going to write n as my number. I'm going to let that represent my number. That's going to be what's called a variable. And n now is going to be my unknown value. And I said that's an important thing to do in problem solving is to identify the unknown. So we've got the unknown identified, and we're going to give it a symbol. And that's going to stand, as I said, for the number. And whatever that number is, that's the thing we don't know. A number. My mouse is working now. Okay, good. And I'm going to type it out from now on because it takes so long to write with my mouse. All right, so we're going to use that symbol n whenever we want to write, whenever we see that phrase number. So what do you got, Oksana? What do you think?
So we got 60 subtracted from 5 times a number. So you're going to do 5n, 5 times n.
5n, okay.
And then you're going to minus 16.
Okay, and let me write that down as you say it. 5n minus 16.
No, it's not minus 16. It's a 16. No, it is 16 subtracted from 5 times the number.
Okay, good.
Equals, okay, so 5n minus 16 equals sign.
Equals?
The number, which is your n, plus 4.
N plus.
Yeah, you're making it, complicated. Not complicated, but something to think about it. That is.
Yeah.
People crazy.
And this is just a tool, and often that's the case. We're going to the more math you know, the more tools that you have to work with to solve problems in your sciences and, of course, your upper level math. So this is kind of the things that you want to build, these experiences, with translating from, the written or oral language into something symbolic form. Then hopefully if you have the algebra skills, you can solve this type of question and come up with the unknown value, your n value. But that was a good translation. 16 subtracted from 5 times the number equals n, the number plus 4. So perfect. What about the next one?
25 is 5 less than 6 times the number diminished by 2.
Yes.
So 25 is 5 less.
So is means equal.
Times
so I'm going to write 25.
Number diminished by, so I guess you're going to do number diminished by 2. So you're going to have n minus 2.
N minus 2, okay.
Yeah, that's the, and then 25 is 5 less. I guess it would do 25 plus 5.
Well, I don't know. Let's just interpret it straight across. Let's see what that does. So
25 is 5 less.
Now remember that that is means equals. So I'm going to write 25 equals.
Equals.
Okay.
5 less than a 6 times. You got me here. I don't know.
Yeah, that's okay. This 5 less than 6 times the number. So we want 5 less than 6 times the number. 5 less than 6 times the number. So that's going to be 6n. Minus 5. That's 5 less.
And then minus 2?
Yeah. No matter how weird it sounds, we're going to interpret what they say. Okay? So we've got that thing there. And then, of course, minus 2. Whoops, my thing is all weird here. There, let me get a space in there.
25 is 5 less than 6 times the number diminished.
Then minus 2. Take 2 more away.
All right.
All right, not bad. Now I might put that 6n minus 5 in parentheses, but we know from simplifying expressions we don't have to do that. It would work just fine here. But that's it, okay? We could do that. Now we're going to find some interesting things when we read these. We might think it's one way and it could be a different way. And there's some ambiguity, and that's because of the language. Mathematics, we don't want any ambiguity. Whatever we do in mathematics, we want it to be interpreted only one way. But when you use the English language or any language, there could be more than one way to interpret something. So it's always good to, what we don't have, unfortunately, is the author, the one who gave us the problem, to ask often, especially if it's written down and is our homework assignment. All right, the next one.
Twice the author? I thought you were the one who made this up.
You thought I was the author. No,
yes, absolutely. Oh,
Dave,
I cannot believe that. Are you copied?
I borrowed these from someone else.
No way.
Yeah. Let's try the next one. Twice, well, maybe.
Twice the quantity of a number plus 2 divided by 6 is 50. All right, so are you going to say 50 equals?
50 equals. I'll write that down.
Yeah. Okay. Quantity of a number.
Okay.
So we'll do n plus 2. So 2n plus 2 divided by 6? Okay. Or you're going to do 2 in parentheses n plus 2.
That's it. I think that is how they're interpreting that. It says
2 open parentheses n plus 2 divided by 6.
That, well, twice the quantity, so that means twice parentheses, number plus 2.
Okay.
And this is what I'm saying. There's some ambiguity in these because like I said, it could be interpreted in a couple different ways. Now, there's some things that often are done with these word problems. For example, commas would be put in there sometimes when we want to separate two different expressions. But they haven't given us that benefit in this case. So we're going to interpret it this way. Twice the quantity of a number plus 2. I'm going to write it in there. And then that divided by 6, right?
Yeah, that's what it said. Okay.
And I think we've got it. Twice the quantity of a number plus 2 divided by 6 is 50. Okay. Here's some examples, algebraic word problems. I'm going to put 2 down here, and we're going to pick one of these to work through. But understanding involves this. Clearly state the given information, so we have to know what is relevant and given in the problem, and use and we're going to use algebraic variables to help us out, and then identify the unknowns, once again using the algebraic approach in order to solve these. So you might have a problem like this, a little more advanced problem. The sum of two positive numbers is 5 times their difference. If one exceeds the other by 7, what are the numbers? Okay, so now this is a problem for us to solve, kind of building on what we just did. A second problem might be this. Find 3 consecutive even integers so that the largest is two times more than the smallest. Okay, so I'm going to do what it says here. It says clearly state the given information. So I'm going to use a technique that's important often for looking back at your word problem and finding the relevant information, okay? So sum of 2 positive numbers is 5 times their difference. Right there is a statement that is in the form of an equation. It almost looks like what we just did previously, trying to interpret a word problem into algebra. Now, a few other important pieces of information is what we're trying to find. In other words, what is the unknown? So what is the unknown in this case?
Well, we have 2 numbers, but we know the difference. So one number is going to be n, or x, and the other one number is going to be n plus 7.
Yeah, I think you've got the idea. And the 2 things that we really don't know are the first number and the second number. And it could be that simple in some problems. And then once we identify those, we want to come up with some algebraic variable, okay, in order to express those. And hopefully there'll be something that in the word problem that tells us what they can be. So we're going to use maybe n for the first one, or x.
Okay.
You see x? Should we use x?
Yeah, that sounds good.
Sure.
But we also want to know that the second number, we can do, instead of 2 variable letters, we can do x and x plus 7.
I like it. I think that's a good idea. And
you don't want to do too many variables.
Because one isn't expressed in terms of the other. So that's always a good thing to look out for, is when your variables, if you have more than one is expressed in terms of the other. So I'm going to write the second one as x exceeds the other by 7 plus 7. Okay.
And here's the sum of them. So we add them together, x plus x plus 7.
Right.
And it says 5 times different.
Yep.
So equals to 5 times x minus x plus 7. But then we gotta make sure to put it in parentheses.
I kind of like this. I'm going to write it.
All right, write it.
Okay. Now these are positive numbers, and one of the things I should mention is whenever you write out in words, and when you do a word problem, start with words to write out your unknowns, and then it'll be easier when you look back and you know whether or not you've answered your question. So when we add these two, it's a sum of two positive. I'm going to write them together. There's the first, plus, as you said, plus the second, which is going to be written as the x plus 7. Let me put a parentheses around that so we can identify it, even though we don't have to. Okay, and you said is equals?
Equal 5.
Yep.
You open your parenthesis.
Yep.
X.
Okay, let me write that down. And,
minus, you open the parenthesis, x plus 7. No, x plus 7 minus x.
Okay, and why did you decide to change it to the?
Because we got to do the difference from the larger one. Because first of all, you said it's a positive number, so if you're going to subtract
I like that.
minus 7, you get a negative.
I think you've got it. You've identified the important part there. That fact they said the positive number, but often when they say difference, it's implied that we take larger minus the smaller often. But in this case, it's really important to do that because we're dealing with positive numbers, not negative numbers. And if you can look ahead. So there we did more than they asked us to do, by the way. They just wanted us to identify the important information and write down the unknowns. Okay. So we've got an equation now. We've come up with a plan. Now, of course, we could solve this equation and then get our answer and see if we answered it. Now, we're just going to leave that for a minute. Let's go to the second one, and maybe we'll finish this one on the next step. But let's just find the unknowns in this case. What are the unknowns?
Consecutive even integers, so that the largest is 2 times more than the smallest. So first of all, they say consecutive and even. So it's going to be n, and the second one's going to be n plus 2.
Well, let's just write that in words. The first one is the first even, right?
Yes.
Let me write that. Let me get back up here. First even number.
Yeah, even number, which is we're going to name it n.
Okay.
You like it n.
Second even number,
Is n plus 2.
Number and the third. You have to, my typing skills are so humor me here. Even number.
And I thought it was going to be n plus 4.
Yeah. Well, I think you're right. We're going to have to write these. If we're going to write them as variables, I might write the first one as n. But if that's an even number, the next even number is 2 away. And I think that's what you said. The next one is going to be n plus 2, right?
Yes.
And then the third one would be 2 more away from that, which would be n plus 2, which is n plus 4. Okay, good. All right, so now I think we've identified our unknowns. We've written a algebraic variable for them because we're going to do an algebraic approach. And now, of course, we could come up with a plan like we did before. We could write an equation and solve it according to what is asked. Okay, so it says find 3 consecutive even integers so that the largest is, etc. I'm going to switch the page, and we're going to find either one, the first one or the second one to solve. Which one do you want to solve? First,
we can do both.
Well, I've got a limited amount of time. That's why I'm saying let's just pick one. I would love to solve all of them. But,
okay, well, let's do. We can do real quick. Well, let's do both.
Okay.
Less than what is it? 60 seconds. You can go back.
Yeah, we've got this almost done. In fact, that one was the one we almost. Whoops, dang it! I'm going to turn back to the other page and let's just finish it here.
So this one is 35. So 2x plus 35. So 2x equals 28, which is your x is 14.
Okay, good.
Bam! Your first x is 14. Your second number is 21.
Am I okay so far or not?
Yeah, you're doing great. Subtract 7 from both sides. Divide by 2. Your x is 14.
Equals. Yeah. Now let's say that somebody gave me this problem, and then you just come back and say x is 14. Now that wouldn't make any sense to them because they don't know what x and all that is. That's what we did for the algebra. That was our plan. Remember, the last step is always to take whatever our plan was and turn it back into English. So I would say not x equals 14 is my answer. I would say for two positive numbers such that that is true, the first number is 14.
And the second one is 21. Okay, very good.
Yeah. So I would.
All right, so in here we have 2n equals n plus 4.
2n. So that the largest is 2 times more than the smallest, which is just 2, is equal to the largest. And the largest in this case is going to be n plus 4, like you said. Perfect.
All right, subtract n from both sides.
Yep. Your algebra stuff. So this, of course, requires that you know algebra.
And your first number is 4. Your second number is 6. And the third number is 8. You did it, Dave.
And double check. And we also should double check to make sure that, it satisfied the condition, So it says that the first is, the largest is 2 times the smallest. And it really is. You can see that the largest number is 2 times the smallest, just to double check to make sure our answer makes sense. So that's it. That was a quick walkthrough of the process of problem solving using the algebraic approach. All right, now, once you feel comfortable with those kind of things, you can move on to the more interesting problems. And I'm just going to kind of run through some possibilities. Now, when you have more experience in mathematics, often you can categorize certain types of problems together. For example, we can have distance problems. An example of this would involve, a distance in time and a rate. And we might know a relationship between that. So a freight train leaves the station traveling at 30 miles per hour. Passenger train leaves 1 hour later traveling at 50 miles per hour. At what time will the passenger train overtake the freight train? Well, there's a typical train problem for you. And we can use our problem-solving skills in order to help us understand that, come up possibly with an equation, solve it, and then see if we have a sensible answer. So those steps we can do. Welcome, Miriam. I see somebody you have joined us. Okay, good. We are doing some problem solving. Miriam, I don't know if you may not have your mic on, but in your chat, maybe you could share what science the highest level science or math classes you're working in right now, because we've got a number of problems to solve. So depending on what you guys are working on, we can take a look at those in our hour workshop here. So if you just type in the chat window, what science or math you're working on, maybe we can talk about some of those topics too, okay? But anyway, this is an example of a distance problem, and we might choose that one to do, or we might choose a coin problem. Really, this is a value number problem, okay? How much of something we have compared to the value of that item. College algebra is a lot of different things. So you're practicing the skill we're using to solve problems, which is the algebraic approach. So Joan bought $5.61 worth of stamps. She bought the same number of 2 and 5 cent stamps, doubled that number of 22-cent stamps, and then the question might be, how many of each kind of stamp did she buy? That's an example of a denomination and value problem, okay? And we might choose that one to do, or we might choose the third one. We're only going to pick one of these three. And this is a work problem. And an example of that might be Bill can mow the lawn in 2 hours. Younger brother Tom can mow it in 3 hours. Both brothers mow the lawn together. How many hours will it take? And we could take a look at how to do that one too, if we wanted to. So out of those three, we need to pick one because I want to do some science word problems here in a minute. So which of those three, any suggestions or any preferences would anybody like to do?
I want to let Miriam pick.
Which one?
I would like Miriam to pick.
Okay, yeah, Miriam, which of those three would you like? The distance problem, the coin problem, or the work problem?
We'll move on to the science one. I don't know. Let's see.
Well, we're definitely going to do a science problem because that's one of the main reasons I'm here. Miriam says that the distance problem looks interesting, so I think let's focus on that. Now we'll take, I think maybe at the end, if we want to come back, we can take a look at the other two because they're interesting too, especially that work problem. That always catches people on homework and on quizzes and exams. Okay, so remember what we're going to do with these. We're going to do this problem. We're going to identify the unknowns. So let's start identifying what we don't know, what we're trying to find in this case. So what is our unknown? What are we trying to find? Well, I'm going to underline some things, so just take a look at it. And if I don't wait for you to answer, that's okay. I just want you to have time to think, what are we trying to find? What's the question? At what time?
Is it a time?
Yeah, at what time will a passenger train overtake the freight train? Now, there's a couple different times going on here. So, but really, that's what we're trying to find. And I'm going to write that down in words. And it's important actually to write these things out in words. So that's what we're going to use as our unknown. And remember, in algebra, we, of course, designate that unknown often with some variable. So we might call that variable t in this case. It's going to be represented by that statement. Time passenger train takes to catch the freight. Okay? All right. So looking back on the question, we have to identify what's relevant in this case. And we notice a couple things. Often in word problems, an important thing to be able to do is to draw a diagram. Sometimes that helps you think. So I'm going to draw a quick little diagram here. I've got a passenger train going, a freight train that left. There it is. It ends up here. It's moving. A passenger train starts out how many hours later? 1 hour later, traveling at 50 miles per hour. A passenger train starts. Okay. Now that freight train is a slower train, it looks like. Notice I'm just trying to understand the problem, miles per hour. And I should always write these out. I guess I didn't in this case. I always like to write miles divided by. Per means division, remember. So I usually write miles divided by hours. Okay. And they reach the important piece of information that one should see from this diagram is they reach the same place at some point, at some time later. So this train has been, this passenger train has been traveling for a time of t. Okay. How long has the freight train been traveling?
T plus 1 hour.
T plus 1 hour. It's traveling, it's been on the tracks an hour longer because it started out first. Now, what I did here was very important, kind of getting that known information written down in a way that kind of makes sense to help us come up with a plan to solve the problem. Now, there's one other important piece of information we might have to do research on in order to solve this problem. And that's an important part of problem solving, is the research. If there's some vocabulary or some formula that we don't know in order to help us solve this problem, we need to look it up, get online, and figure things out, ask somebody that knows. But do our research. And there's a piece of information missing. We need a relationship between the time, the distance, and the rate, because the distance is the same for both of these. So that's what I would do if I didn't know the formula, of course, for time, distance, and rate. But of course I do. And I'm going to write that down. Whoops. My mouse is crazy.
They would not be the equal, like t plus 1 times 30 equals 50t?
Isn't that crazy? Well, that would be true if we knew that formula. Remember, the distance is equal to rate times time, right? Do you know that formula?
Yeah, but you already lined that up. You said 1 is t plus 1 hour, and then t goes at 30 miles an hour. So, and they have to be equal, right?
I think you've got the idea. Yeah. And that's exactly it. If they travel the same distance and we've got an expression for the time and the rate, look how easy it is. So once we know that this is true, distance is equal to rate times time. Notice I just put symbols there just to save on me trying to type it out. But I should really spell it out because I think most of us know this, especially if Miriam is doing college algebra. She's run into this formula, I'm sure. We've got d, of course, is distance, r, of course, is rate, and t, of course, is time. And so there we got it. And it's exactly what Oksana said. We can just put the one equal to the other. We said the distances are equal. So I'm going to write that down. That's going to be, whoops, let me get my pen back. Here it is. I got it. Okay, good. And that's going to be 30 times, that's the rate, times the time of t plus 1. Distances are equal. That's the distance the freight train traveled is going to equal the distance that the passenger train traveled. Rate times the time. Time is unknown in this case. And so now we've got an algebraic expression, or an algebraic equation that models the problem that we've just presented. And we can, of course, solve that now. And I'm going to do that. And hopefully come up with an answer. Now, everybody's problem solving or algebra skills are the same as, the same as mine here. So we know that we're going to subtract 30 from both sides, which is going to give us 30 equals 20t. And then, of course, what are we going to do next? Divide by 20. And we get t is equal to 30 divided by 20, which is 3/2 or 1.5. And if you just said that as your answer, you're not done yet, because remember that fourth step is also very important in problem solving. That final step is to describe your answer in words. Well, the words are up here already. I wrote them down at the beginning. That helps me out. The time passenger train takes to catch the freight train is going to be 1.5 what? Minutes, hours, seconds, what? Well, since we had miles per hour, our answer is going to be hours. So we've got 1.5 hours. And since I've already written the words up here, it's going to take 1.5 hours for the passenger train to catch up with the freight train once it starts out. As a follow-up question, we could ask, how long has the freight train been traveling?
2.5 hours?
Yeah, 2.5 hours. Mary, I'm sorry, I didn't see your post down there, but it looks, yes, I am recording this and you'll be able to view this recording later, okay? Sorry, I missed your chat window. Nothing down there. Okay, so yeah, I think we did a good job in addressing this question. I think we satisfied the, okay, great, Mary. And there's our great problem. I'm going to take a look in the last 15 minutes we have here. Now, we're going to have enough time, but let's see how this translates over into science questions. So far, we've looked at a few math problems, and we've practiced with the procedure for problem solving, and understand the problem, come up with a plan, carry the plan out, and then make sure the answers make sense. Okay, so we've done that. Now, of course, there's more to be said about those 4 steps. And in terms of the sciences, we're still going to use that same idea. And it's going to be doubly important to identify the unknowns in our problem-solving process. Okay, so that identifying the unknowns is still going to be an important thing to do. Okay. Labeled diagrams is also often important, especially in the physics, right? Manny, you've done the thing on free body diagrams, etc. And that's one of the things that we probably have to do in this case. Right. So in this case, a couple other things that we might want to do for the sciences is research unknown symbols, vocabulary, and concepts. When I would get stuck on science problems, it was because there was some word in there I didn't know. So I'd keep on trying to throw numbers at it. I'd find a formula, I'd throw some numbers in there, and it never worked. And the reason was because this one word I didn't understand, I assumed it was something, was keeping me from understanding the entire problem. So my suggestion is when you do science word problems, make sure if there's any vocabulary you don't understand, figure it out. If there's some formula that you might need, find it. Okay, so you need to do research. You might have to do some assumptions in order to help figure out what you're going to do. So we're going to do all of that with this one. I'm going to read it. At least we're going to set it up. We're not going to completely solve this one. We're just going to set it up, draw a diagram, and get it ready. 90%, sometimes 90% of your struggle in applications and word problems is understanding it. 10-kilogram box is pulled up a ramp that is an angle of 20 degrees with a horizontal. With a rope that makes an angle of 30 degrees with the ramp, if pulling box is pulled up a ramp at an angle of degrees of 30 with a rope that makes an angle of 30 degrees with the ramp. If pulling with a force of 70 newtons causes the acceleration of 2 meters per second squared, find the coefficient of friction. There's all kinds of things in there. Unless you've taken a physics course, a lot of this you don't understand. So you won't even attempt it. Of course, when you take your physics course, you would have talked about these concepts already. So if any of these ideas, for example, acceleration, you didn't know what that is, you'd go back and review it. If that end there didn't make sense to you, you didn't know what that unit was, you'd go back and figure it out. Coefficient of friction, if you didn't know what that was, of course, you'd go back and review that. So those are some of the research you'd have to do in order to figure out how to do a problem. And it might take you a day to do that. Hopefully that's not on your exam at that moment, but to actually do this problem and you start out with some things you don't know, it takes some time. All right, I'm going to draw a diagram. This type of problem begs for a diagram, so I'm going to do that. I'm going to make it a different color. I'm tired. I don't know why I get stuck on red, but I did. All right, so let's get rid of that for a minute. I wonder if I can undo it. There it is. Okay. And there's my ramp. I'm going to draw it up here real quick. And remember, this problem I'm just going to set up. And I'm going to draw it freehand from here on out. Okay. Oops. There we go. Okay, so here's my box on the ramp. And that didn't look much. Oops, that didn't look much. Dang you, ramp. There it is. That's my mass. That's my box on the ramp. It's a bit crumpled. You don't have to worry about that too much. It's okay. All right. And then I'm going to be pulling up on it in this direction right here, okay, with a certain force. And so in physics, it's often important to, of course, draw out your figure, because you can label most of the important known values and help identify the unknowns by doing it this way. So our box here, we're pulling it up the ramp. I'm going to put some labels in there. Let me do it one more time here. Oh, no, come on. All right, and there's the level ground. All right, so according to this, it makes 20 degrees. A box is pulled up a ramp at an angle of 20 degrees. And then the angle the rope makes with the box, with the ramp itself, is 30 degrees. So I'm going to label that in here. There's 20 degrees. These are my knowns. These are my relevant or important known things in the problem. And this is 30 degrees. I know this force. I know from physics that's a vector quantity is going to be equal to 70 newtons. And I'm not putting my precision values in here right now. I'm just putting in the numbers, but that 70.0 is going to be important when we look at our final results. Also, what else do we know? Well, we know the mass of this box is going to be 10 kilograms. I'm going to put that in there. Just write it in my diagram. And once again, we had to know that that was mass. And one last thing, in terms of the relevant information, there's an acceleration of 2 meters per second up the ramp. I'm going to put that in red. Okay, so we've got an acceleration up the ramp of 2 meters per second. Per second squared, sorry. Okay. And so that's kind of a sloppy diagram, but if I was doing this with a pencil at home, it would look a little bit better, but not a whole lot better. All right. I still haven't identified the unknown. What is the unknown in this case? What am I trying to find? What is my unknown?
Friction. Coefficient of friction, you said.
Yeah, coefficient of friction is what I'm trying to find in this case. And once again, since we are studying this in our book right now in physics, we know the symbol that goes with this. And the question I have to ask myself, I know there's two types of coefficient of friction. There's a static and there's a kinetic. So once again, I have to think about this and decide which of those two makes sense with the problem. So there's all kinds of things that we have to do. Now, one of the clues is we do have an acceleration, so it is moving up the ramp. Therefore, I decided the coefficient of friction is going to be the kinetic. It's in motion, okay? So that's crazy. That's a crazy amount of work. Now, I did it very quickly, which really, this might take me, if I just ran into this problem without having done it before, it would take me a while to think this through. The diagram is going to be super helpful in coming up with a plan. Remember, that's why I did the diagram. It puts relevant information right at my fingertips. And then, of course, also a very important feature is to identify clearly the unknown. And I should write that out in words like I said. I mean, this is a coefficient of, but kinetic friction. Okay. And there it is. I've done pretty much the understanding the problem for this. Now, that's only the beginning. Of course, if I want to solve this now, I have to come up with a plan. Now, my plan would be this. If I was going to solve this, my plan would probably be do a free body diagram and use, and I'll just give kind of, I'm not going to do this completely, but to give a hint, what I would do next is just do a free body diagram, and then I would use Newton's second law. Sum of forces is equal to mass times acceleration. Okay, so that suggests what I should do just from understanding the problem. You have to forgive me for kind of moving through this a bit, but we have one more science problem to look at. And Oksana, you like the chemistry, right? So we are going to finish with a chemistry problem right here.
Okay, let's go.
Yeah, and I'm going to write this one down. Once again, we're starting back at the beginning. We're going to try to understand this problem, and we have to carry into it some things that we know. So this would be me and a chemistry student. I already talked, I read the chapter on equilibrium. I know what concentrations are. I know what Kc represents, the equilibrium constant. And so I look through the problem, and I look and see if there's any concepts I don't understand in here. So I'm looking at things. I see things like dinitrogen tetraoxide. So I have to know what that chemical formula is for that. I have to know what the formula is for nitrogen dioxide. Okay. These are gases. So if I'm going to write something down here, I would start with a balanced equation, because I know that's one of the things one does to help you understand problems in chemistry, especially ones where we have equilibrium. We're going to need a balanced equation. So step one would be to come up with a balanced equation for the reaction that is being expressed here. Okay, so dinitrogen trioxide, I'm going to make this in black. No, let's make it in blue. That's okay. So I've got two nitrogens. This is dinitrogen. Tetraoxide, sorry. Tetra means 4. And since this is an equilibrium problem, I know this. But if I didn't know that, I would have to do some research or read my chapter again that I'm working on this homework assignment on, or this problem to solve. Yields, and this is my product side, is going to be nitrogen dioxide. Okay. So that's where I'm going to start. I'm trying to understand this problem. So step one was going to find a balance equation. Well, this is not quite balanced yet, so I still have to do that. And I see on the right-hand side, I have two nitrogens over here, or sorry, one nitrogen over here, and on the left, 2. So I'm going to attempt to put a 2. Oops, come on. My crayons, there we are. I put 2 over here, and then double check. That gives me 2 on the right, 2 on the left, 4 oxygen on the right, 4 on the left. I've got a balanced equation. The phases of these substances are gases, so I might put in the phase underneath just to complete my reaction, my formula for the reaction. Okay. And that would be my first step in this. Now, I know it's an equilibrium, so I, at this point, know a technique called the Rice technique in order to solve this problem. And I would have to, of course, if I'm going to do that, that suggests that I have things like the initial concentrations and then come up with a statement for the final concentrations. So I'm going to do the Rice stuff, which is the reaction, the initial values, the change, as this reaction runs. And then at some point, the reaction to the right is going to be the same as the reaction to the left, and we end up with an equilibrium. So there it is. There's my game plan from things that I am given, okay? That would be the second thing that I do right there. That would be kind of step 2, and it would require some of the information that I know. And that information, for example, is that I'm just going to write down some things. The temperature is the same for both. Now that's an important piece of information, but this number is not a number that I'm going to use in my calculations. So often in word problems, there are going to be numbers that are important for a description, but they're not necessarily used in the calculation. And sometimes that makes it super hard to figure out which numbers to use and which numbers not to use. But the equilibrium constant is given. So I'm going to put that down as something else I know. And we may not get this completely solved, but I do have an answer that we will look at to double check. A look at the precision of that. In chemistry, we talk about sig figs, so that's going to be important in our answer. And we're going to have to round it to the proper number of sig figs. And the accuracy. So the accuracy, we might look back and see if our number makes sense with everything else that was given. So we could double check our work. Now, I'm not going to do that because my time is running short and I'm almost done. And if you want some of these problems to play with, right, I'm going to email them to everybody that attended the workshop, and you can take a look and play with these problems yourself. All right?
Okay, sounds good. Thank you, Dave.
Okay. Let me recap, and we'll be done. And you can see I had all kinds of other ones to do, but of course, in an hour, we are not going to get to any more today. Okay. To recap quickly, clearly state the given information. This is an important thing. This takes up a lot of time understanding the problem. Identify the unknowns. If needed, draw and label diagrams. We've seen that in the physics problem. Research unknown symbols, vocabulary, concepts that the problem assumes you know. If you don't know them, spend time understanding them. Devise a plan. We use the algebraic technique, but there could be other things. Maybe you have a formula or a function that you can just put your known values in and come up with an unknown, and then, of course, test it out. Write or find a program. You might have some programming to do to model or simulate the problem. And then, of course, make sure you have the skills to carry out. We need to have algebraic skills, of course, to finish this, to finish some of those problems that we started. Finally, this is important too. Don't skip on this step. Look back and check and interpret what you have done. Once you devise a plan and carry it out, check to see if you have a suitable answer. In other words, suitable means proper precision with the proper units. And you want to make sure that that answer is reasonable, and that involves the accuracy. In other words, close to the expected value you expected. For example, if you're talking about some child's shoe size that you're doing an experiment on, and you have an answer of 5 feet, you've done something wrong. So make sure that it makes sense. Did you answer the original question? Go back and make sure. Maybe there's 2 parts to the question. And finally, be sure to be able to describe the answer in words. The word problem starts in words. Your answer should end in words. All right, I've had my say, I guess, about word problems. I hope you enjoyed. Once again, I'll send out some of these fun problems that we worked on to you by email.
All right, sounds good. Thank you so much. Excellent presentation, Dave.